thanks so much for being here. It's great to see this big turnout. I'm really pleased to have a chance to welcome Holger Hoos here. He's, as many of you know, was a longtime professor here at the Department of Computer Science at UBC, and was a close friend and collaborator of mine over many years. We were very sad to see him go when he left first to Leiden in the Netherlands, and then shortly afterwards to Aachen in Germany, where he took up a big fancy professorship leading their AI initiatives in Germany. Holger has been increasingly involved in community organization in AI, having led the Canadian AI Association and then spearheading some of the critical AI initiatives both in Germany and more broadly in Europe. He's also a really distinguished researcher who has worked on a whole series of important topics in AI, originally around kind of heuristic optimization methods, then kind of moving into meta-algorithmic methods that use AI to design these sorts of heuristic algorithms, and then moving again into the similar sort of automatic outer loop approaches that optimize machine learning methods. And that's a wide range of different awards, including fellowships in CAIDA and this time, let's all welcome.
This very kind introduction, Kevin. Of course, I'm thrilled to be here again at UBC. I do show up every few years. Of course, the pandemic has disrupted this a little bit, and last time I was here was for AAAI downtown, so I didn't make it to campus. My apologies for that, but wonderful to be here right now. So first of all, who here has ever heard of Aachen? Well, oh wow, that's many more than I thought. So maybe what I'm about to do next is then not really necessary. But I thought for those of you who don't know where Aachen is, I'm going to quickly show you. So now let's hope that Google is doing its thing. And you know, I mean, Aachen is very well known for its cathedral and for the fact that Charlemagne ruled Europe from there about 1,000 years ago. And so let's just quickly go over there so that you have an idea what this is like. So of course you all know what this all looks like, or a little bit higher up, and then obviously we're going to have to cross Canada and the Atlantic, which will happen shortly, and we're going to somehow fly over a major bit of Europe, and you can see where Aachen is interestingly located. And you know, for me personally, it was always great here. It's also great over there, and the reason why it's great over there is because Aachen is really at the very heart of Europe and at the heart of the European enterprise, not only because Charlemagne was the first who kind of unified Europe in some sense, but also because there Aachen is sitting right at the border between Germany, Belgium, and the Netherlands. So from where I work and where I live, I can walk to Belgium, I can walk to the Netherlands, and it doesn't take many days, but basically an hour or so. So that's kind of cool. It is also a pretty interesting place, and I thought in order to just give you a little bit of a visual thing and also show you a little bit what we're trying to do with the AI Center is to generate enthusiasm for AI. Of course, critical enthusiasm. We don't want to just wholesale buy into all the hot air that's currently being produced by many people in the industry. But of course, there's much to be excited about. And so this is from an event that we had run in 2023. At the very center of Aachen. So what you see back there is a crowd of around 800 people or so. And that was basically the opening of our Aachen AI Week, which is a big event that's now running every 2 years. And what we've done there for the very first time, you can see that up here. worse is that if anything goes wrong, the air is not still. It wasn't still that evening. If anything goes wrong, they will bump into each other and then they might fall from 100 meters high. These don't weigh very much, but you can imagine that this is a problem, right? So, and you know very well that, for instance, in Ukraine, where drones like that, unfortunately, are used for warfare, they're being majorly programmed using machine learning. And so it becomes very important to trust the machine learning methods that you're using in applications such as this. And in some sense, this is exactly what my talk today is about. I was very tempted to give you a presentation on why LLMs are not the answer to life, the universe, and everything. In fact, to use LLMs to program drones, truly terrible things would happen. And unfortunately, I predict that all of us will see some of these terrible things happen because people believe when certain people in the industry say, you don't need to learn programming anymore, you don't need to learn machine learning anymore, because LLMs are going to do it all for you, right? That is, let me be very clear, bullshit. It's dangerous bullshit, and we should, as computer scientists, not buy into it. So I won't talk about that today. Plus, we all know what the answer to life, the universe, and everything is. It's 42, right? But instead, I want to talk about learning, reasoning, and optimization, three broad areas within AI that I've been working on over the years, as Kevin said, and in particular, how they relate to adversarial robustness of neural networks, which is one of the things that you have to worry about when using neural networks and neural network-based technology in safety-critical applications. So before going there, I'd like to just very briefly explain to you that I think the nature of the AI revolution is not really machine learning or LLMs or Gen AI, but it's actually to go from manually constructed algorithms for doing stuff to the automatic adaptation to a given set or distribution of inputs. And machine learning does that, but it's not the only method for doing that, right? So I think that's important. What's even more important is that by doing this, you can automate programming and parts of programming. And again, I don't mean LLMs for code generation. That can be done and it has its issues, but generally the idea of automating part of programming tasks. And what's really interesting is that if you look back, why did Microsoft, for example, buy OpenAI? They were very clear what they really had in mind. They didn't want ChatGPT. They wanted to automate programming. Now, good. So the key idea behind the automation of programming, and particularly the work that I've been doing together with Kevin and many other colleagues, is to automate the analysis and design of algorithms using methods from machine learning, statistics, and optimization. Yeah? And in our work, this has taken the form of empirical performance models. That's something that Kevin and I did here together at UBC. Kevin had started a little bit earlier, and then we sort of got together, and that was a really pleasant and very effective time that we had together with our students here. So we could say, I think, state-of-the-art empirical performance models were born here at UBC and then conquered the world from there. And the same could be said for automated algorithm selection and configuration and a few other techniques along those lines. Very important special cases here are automated machine learning and more generally automated AI, which is the automated analysis and design of ML or AI algorithms. And you would want to do that because, as you all know, AI expertise and machine learning expertise is kind of difficult to acquire. There is a perpetual shortage of it. And if you can enable people who have expertise, but maybe not top expertise, to do better using computation, then this is a good thing. So today I want to focus on neural network robustness, as I've motivated before. And basically, that starts from the observation, as probably everybody here knows, that neural networks, as sort of the key ML technology underlying most ML systems that you would be using today, not all of them, but most of them, they tend to be very sensitive to input perturbations. So this lack of robustness has been known for at least 10 years. And in particular, these neural networks are vulnerable to adversarial attacks. An adversarial attack is when you take an input to a neural network and you perturb it just a tiny bit, maybe imperceptibly, and then you get a different output, one that is potentially disastrously misleading. So here's such an example. I already saw somebody walking in with a violin, perhaps. Is it a violin?
Viola, but yeah.
Viola, even better. Man, I love it. So viola and horn, by the way, they go very nicely together. So we'll start with this picture of a French horn, and this other picture, which for you will look exactly the same. So it's basically very subtly manipulated, but a pretty state-of-the-art image classifier classifies the right one as a hot dog. That's pretty incredible, right? And moreover, if you do this to this stop sign, and this is sort of realistic footage, you wonder why it's so pixelated. That's because that's what an autonomous car might see. Well, maybe not the latest generation Tesla, but some autonomous cars might see exactly that. And if you manipulate it just a tiny bit, we still see a stop sign, and the algorithm sees 120 kilometers per hour. That's very bad. Yes?
Yeah, this is tested on one algorithm or multiple?
You can construct these deceptive examples so that they're deceptive for multiple algorithms. Typically, you do it for one algorithm, and in this case, it's enough if you do it for the one that's in your Tesla, for example, right? But they can generalize indeed. Good. So I want to show you a little demo because this doesn't just work with images, right? For images, it's been studied for quite a while, and that's the most prominent application of this. But I want to show you that this also works for audio, which is interesting. So we're going to start with this one here. So this is a little recording from some audio database. You probably recognize what it is. It's a crow, right? So unfortunately, it's again, the system here makes it a little choppy. It is a crow. And now if you basically apply a filter to this, a very carefully constructed audio filter, which is a way of manipulating an audio signal, then you get this. It's pretty much the same to us, right? So this is characterized as crow, and this one here as a frog, right? So the filter is sort of a crow-frog thing. And that works for many different examples. My favorite one, I think, is here. So that would be a pig, actually. It sounds scary, right? So be careful of pigs. And but indeed, this one is classified as a sheep. So you don't want to meet that sheep, I think. Anyway, so this can be done from many examples: audio, video, images, and so on. So it's a pretty broadly encountered phenomenon. And so, what do we do about this? Well, one angle at going at these things is to use formal reasoning techniques for so-called robustness verification. And I'll talk in more detail about what that is, but the key idea is you have a neural network and you kind of want to formally prove that stuff like what I've just, like the phenomena that I just demonstrated, you can't happen, mathematically can't happen, right? And so one very well-known approach is so-called local robustness in classifiers. You might ask, is there also global robustness? Yes, it's much harder. I won't talk about it today, but local robustness already is a good thing. And here the key idea is to ensure that all x close to some given input x0 are classified with the same correct label. And we'll also stick to classification problems for today because they're clearly important enough that they deserve attention. And you can do similar stuff for regression, but that would go beyond the scope of this talk. Mathematically, it looks like this for all inputs x, that according to, for instance, the L infinity norm are within a certain bounded distance epsilon from each other, right? What you want is that the labels are the same, okay? And then, of course, it depends a little bit on epsilon, how robust this thing really is in practice. So that is a challenging problem. And why is that? Well, first of all, there are diverse network architectures, many different layer operations, many different activation functions, and the list goes on and on and on, right? So whatever you do in order to mathematically establish this property down here, you have to take many factors into account. And then there are also diverse verification algorithms and approaches, for instance, based on mixed integer programming, satisfiability modular theories, specialized branch and bound techniques, and many others, right? And of course, you recognize that these are sort of pretty generic AI-ish OR techniques that can be used for many interesting applications, but definitely also for this one. And it won't surprise you if you see how people go about this, that you might learn that also this problem is actually NP-hard, right? So it's actually much harder than the learning problem itself. So now I want to basically talk about three things for the remainder of the time that we have together today. The first of them is, what is even the state of the art in neural network verification? Can we do things? And if so, what does this look like? So here the situation is as follows. These verification methods are typically evaluated on a relatively small number of benchmarks, and that's because it's expensive. And against some different and sometimes ill-specified baselines. That is a situation that in other areas of AI has been encountered also, and then people have, put effort into designing better competitions and better evaluation protocols and so on. And indeed, there has been a competition here since 2020, so a relatively new thing, that seeks to determine a winner, sort of the best robustness verification algorithm based on some performance ranking, right? So that people have been doing that. And so when we started looking into this problem in my group in Aachen and Leiden, the first thing is we said these benchmarks are a little small, so let's actually construct a new benchmark so we have a better idea how good the stuff really is. And so we assembled a large and diverse set of benchmarks consisting of 79 image classifiers. The audio work is newer, it's actually ours, so we didn't have these classifiers then. We do now use them as well. And also quite a few different verifiers. So 8 CPU-based and GPU-based verifiers. You can use GPUs to also accelerate the verification process, but you don't have to do that. And then step 2, very, very standard, was an in-depth empirical evaluation. And here's what we found. So these are CPU-based methods, random networks on CFAR, right? So CFAR is not the most exciting benchmark in the world, but hey, it's Canadian, so we like it. And hey, it's also been studied to death, so there is a lot known about that. So it's actually a very thoroughly understood benchmark. So here are the different verifiers. I won't explain them in detail, but you can see that, they're not that old. And here's the number of instances solved within some cutoff time of 1 hour on this particular machine. And you can clearly see that there is a winner, and it's not even particularly close, right? So this one takes gold, and there is a second, which is not far behind, but significantly, and then the rest is a lot worse, right? So this is what that landscape looks like. So now as a practitioner, you might go and say, let's try throw Neurify on this thing, and based on this, maybe that has a good chance of working. But now if you look at the instances, right, an instance here means basically a classifier and an image, right? And we want to see is the classifier robust with respect to this image, and then you have to do this for many images, right? So every data point here is one image, and they're all for one classifier. And this is the CPU time that Neurify takes to verify this. And this is the CPU time here that this variant, so the silver medal winner takes. And lo and behold, one doesn't dominate the other, right? One is better than the other, but there's no domination. There are many cases where actually the number 2 ranked is better than the number 1 ranked. And if you look at a different classifier here in orange, you get the same picture. And if you look at all the classifiers we studied together, you get again the same picture, right? So this happens for all classifiers and for quite a few instances. And then also if you look at different epsilon values, remember epsilon is the amount of robustness, the amount of perturbation you want to tolerate. So you can increase this 5-fold from this very small value to 5 times the very small value. It's still the same picture. And if you look at GPU-based methods, it's still the same picture. So this happens all the time. Now, this is kind of interesting because it means there is no single best verifier, right? And instead there's performance complementarity, which is a great starting point for all sorts of interesting techniques. And that holds for CPU and GPU-based methods, different networks, different data sets, and different epsilons. So it seems to be the standard. And also, not all verifiers actually work on all network types. I didn't show you data for that, but some of the verifiers simply crash on some network types. And that means, of course, there's major potential for the kind of things that Kevin and I and many others have been studying for years, which is parallel portfolios and algorithm selection. So that was good to see. Nobody else knew this before. And we actually demonstrated this pretty thoroughly in 2023 and then extended the work and published it relatively recently in JMLR. So that's the first thing, right? So the state of the art is more complex than one thinks, and there's good reasons to not put all your eggs into one basket, but to have a diversity of methods and approaches and then somehow try to exploit that. The next thing, Kevin also won't be surprised because that's exactly what he would have done, is to ask about verifier parameters. Because these verifiers, of course, they solve NP-hard problems, so they have all sorts of settings. And these settings matter in terms of how efficient they are in particular situations, on particular networks and images. So of course, people like Kevin and I, and hopefully you as well, would use automated algorithm configuration to optimize the performance. Why not? I mean, the techniques are readily available. Yeah, it costs some computation, but it's much more effective than twiddling parameters by hand, and you typically do get major performance boosts. And the interesting thing is, here, we could show that this works, but only when you combine it with parallel portfolios for two very well-known verifiers, MidVerify, which you've seen before, and Venus. Now, the interesting thing is when we try to optimize them individually, just one, and then run the optimized configuration, we couldn't get any improvements. And it's sort of the mystery why that is. I would have totally expected to get an improvement, but we didn't. But then when you actually allow for more than one configuration, you do get nice speed ups. And that's actually the first piece of work that we did in 2022 on robustness verification. So that encourages us to go further. So Kevin can tune out for the next little while because you will know all of this, but for the rest of you, it's hopefully a little bit new. So automated algorithm configuration is this idea: you have an algorithm, here's this machine with the gears, and you have some controls, and they can be discrete or they can be continuous, right? And they are parameters that control the performance, not the way this thing works, but how efficient it is, right? And then you can automatically also measure performance, right? And so if you twiddle with these settings, then performance can go up or down, right? That's a pretty standard situation. And so this can be formalized as the so-called algorithm configuration problem, where given a parameterized, we call that a target algorithm because that's our target for later optimization, with some configuration space C, which is typically combinatorial and very large, and some set of training inputs, and some performance metric, which for instance here could be the time it takes to verify something. And we assume without loss of generality that this is to be minimized, but maximization is really the same. What we want to do is determine this argument. And as Kevin and I figured out together with our students, this isn't exactly an easy thing. This can be arbitrarily challenging, but also arbitrarily rewarding in a sense. And so it's challenging because the configuration spaces, as I already mentioned in passing, are very large. They are discrete and categorical parameters. The parameters interact, and some parameters can even be conditional on others. In order to imagine why this might occur is you might imagine that there's an optional component of an algorithm and it has parameters, right? And then there's one parameter that says use the optional component or not, right? And then all the optional components parameters are conditional on the optional component even being used at all. So they're complicated dependencies. And that means standard optimization methods actually don't do it usually. So you have to be more sophisticated, which is why one of our PhD students who actually made a career with this spent, what was it, Kevin, 6 years or so to get a particular approach to work. And when it worked, it was great, but 6 years. But effective general purpose algorithm configuration procedures actually do exist, as we could show together here, and as has been shown by many others in the years that followed. So here's an example that is somewhat relevant in what follows. This is a so-called mixed integer programming problem. Who has heard about these before? Okay, the rest of you should hear about them. I'm glad you do today, and maybe you want to learn more because they're incredibly useful. So let's say we want to maximize this expression x plus y, but we also have some constraints, right? And in this case, we have linear inequality constraints. And then I have no idea why this is mixed, that little sign here. I don't see this on my slides, but of course this is greater or equal than 0, what you see here, right? And so then you add one more constraint, x, y should also be integers. And that extra constraint, so this can be solved, this is basically an integer programming problem that can be solved in polynomial time, but with this constraint, it becomes NP-hard. There are many, many problems in industry that can be reduced to this form, so encoded as something like this, so it's useful. Widely used to model and solve real-world optimization problems. Very powerful commercial solvers exist. Cplex, Gorobi, maybe you've heard some of these. Very, very useful and widely used tools. And this problem has been studied intensely since the 1960s. It's NP-hard, as I said, and it's solved effectively using an amazing mix of sophisticated and highly heuristic branch and cut algorithms. I don't want to go into details, but it's amazingly complex. If you think deep learning is complex, look at this, and it's at least as complex. And we really do need to use cutting-edge solvers, and they use optimization to find good solutions, right? So this is optimization technology. And they also use automated reasoning inside to prove optimality or infeasibility. So they prove using automated reasoning, specific automated reasoning techniques, that no better solution can exist than the best one you found using optimization. So they're a great example of how combining automated reasoning and optimization can give you the power to solve many real-world problems, notably NP-hard real-world problems. So when you want to solve these mixed integer programming problems, there are many challenges. The computational complexity, right? Many real-world MIP instances are actually relatively easy, and that's why these tools exist and are being sold and used widely. But others, for reasons that nobody really understands, because they look just like the easy ones, cannot be solved within reasonable time with anything that people have thought of so far. So it's very intriguing. The solvers are highly complex and configurable via many parameters, hundreds of parameters, and the settings can have a huge impact on solving times. And then many types of MIP instances require different solver configurations, which makes this a great target for algorithm configuration, which I talked about before. And that's, of course, why Kevin and I and others applied algorithm configuration to MIP solvers. I should also be honest about the fact that there's very limited understanding still of what works when and why, which is very unfortunate. And automated algorithm configuration can help a bit to understand this better, but hasn't really solved that mystery either. I think the reason why this happens is the reason why we are still so relatively unclear about how to go in general about NP-hard problems, right? It seems to be a mystery at the bottom of NP-hardness. In any case, one of the problems that Kevin, I, and our back then PhD student Frank Hutter, now a very prominent ML researcher internationally and especially in Europe, in 2010, so 15 years ago, we looked at these wildlife corridor design problems that are natural conservation problems with some really nice real-world applications. Every cross here on this scatter plot is one instance of that problem. So sort of one way of buying parcels of land in order to sort of get ecological benefits. And here's the time that the Cplex commercial solver takes in its default configuration out of the box, how many people use it to solve these instances. And here's the time for an optimized version of Cplex. And this one was actually automatically configured by us, by our solver. And as you can see, for easy instances, this doesn't make a big difference, right? But for hard instances, you get orders of magnitude of speed up. And overall, if you average across all of these, it's a 52.3-fold speed up on average. So I would challenge each of you to take, some favorite algorithm and speed it up by 52.3 times. You will find that this is usually hard, right? And here, it was basically an automatic method that achieved it, which is nice. And so now we can do the same thing for these local robustness verification problems, and here is how we did it. So basically here you have a neural network, and here you have an example, in this case a pig, that gives you together a verification problem, and then you have this MIP solver that basically is set up inside the verification engine to basically prove that such a perturbation cannot exist, that this is then misclassified within a certain epsilon radius. And what we do is we have multiple optimized configurations of the MIP solver, in this case here Robi, and in a parallel portfolio, and whichever solves it first, because this is a correct sounding complete algorithm, right? Whichever solves it first stops the entire process and then says either it's infeasible, meaning that the network is robust for this input, or it's not robust. Okay. So that works very nicely. And then, of course, the parallel approach has some overhead. So you see quite a few of the points here lie above this line of equal computing time. This is the computing time for this little portfolio consisting of optimized configurations. And this is the computing time of the default version of the verification tool. But you can see in many, many, many cases, first of all, we can now solve instances for which the default timed out. There are also a few instances for which the opposite is the case. And from many other instances, we get basically an order of magnitude improvement, which is very nice. So par 10 score, which is where you penalize timed out runs with a factor of 10, drops from 2,900 to 1,800. So that's not 50-fold, but that's still very significant, right? Good. And then when you basically do this for in slightly different situations, you get, of course, similar results. So this is MIP verify on a very well-known neural network called SDPD MLPA. And here the part 10 drops even further from about 40,000 to just over 8,000. So that's kind of nice to see. So this generalizes. Now, at RWTH this year, we had an interesting piece of work together with two of my PhD students, one in Leiden, Matthias König, and one in Aachen, Konstantin Kaun, who had just started actually. And they showed that there are further efficiency gains in this possible via predicting timeouts of these solver configurations. And the key idea is to basically use a supervised machine learning method to predict whether a verifier would time out, given some timeout, right, like 1 hour, on a given robustness instance, and then you terminate the runs that are predicted to time out anyway, right? So you don't run them for an hour. You predict this will time out, and you either don't run it at all or run it for a little bit, just as a little insurance policy, but then terminate it. And so what you find here is this doesn't come out too well, so I'm going to explain it to you. This is 3 measures of accuracy. So we have accuracy 1 here, and this is actually precision, recall, and accuracy between 3 different approaches. And you can see that, I don't want to go into the details, we get very good accuracy with these methods in predicting timeouts, right? It's not perfect, but it's good enough to be useful. And then what you see is when you actually look at the curve of running times on these instances, this is the blue curve, and you then apply our timeouts, then you get a 21-fold speedup. So this entire curve just shifts, which is very, very nice. And the same holds here for a much more challenging problem where the speedup then is only 3-fold, but that's still very significant. So this is, by the way, a ResNet architecture on ImageNet. So that's already a reasonably challenging problem, right? So this really works quite well. Yes, please.
So I don't know if you will explain it, but how do you compute the parameters to speed it up? Like, do you do it on the data set that you perform very fast? Like,
Excellent question. You have to do this on data where you have reasons to believe that it resembles the data that you ultimately want to run on. So in that sense, algorithm configuration is like supervised learning, right? However, interestingly enough, unlike many supervised learning methods, this tends to generalize reasonably well, right? So that means if you have instances that are a little bit different, you don't all of a sudden catastrophically lose all the advantage. Of course, if the instances are very different, then it might not work at all. But yes, you have to have access to some instances that are similar to the ones that you believe to encounter in practice, right? And if you don't have that, you need different techniques, which I don't talk about here. Yeah.
So I mean, the follow-up to that always, as soon as you have images, is what is the distribution of images? We can all write what mathematically it means, but no one can ever
Absolutely. And we can discuss it later if you wish, but all I want to point out is if you question that this is always possible, as you should, as I do as well, then you should never use supervised learning in the first place, not even for training your image classifier. And then you're in a different world than the one I'm talking about here and the one that is used quite a bit out there in practice, right? But yes, this is a problem. Kevin, you wanted to say something?
Yeah, I just wondered if you could tell us how you trained the you configured the parallel portfolios. Did you train the parameters jointly, or did you do them sequentially? Or
no, we did it the way that you and I figured out a long while ago. We first trained one and then the other to optimally complement the first.
So I just wondered if you had new ideas on that since then.
I do have new ideas, but here we wanted to show, even if you don't have new ideas, you already get really good results. And yes, I think if you do it jointly, which for 2 you could actually, you would certainly get even better results. Yeah? Good. Alan?
Just a follow up on this. I was really puzzled when you said that you did not see performance improvements optimized 1 by 1. And you have to do this jointly.
Yes.
To get the and that struck me as impossible. But I guess what I'm hearing from you, like mathematically, that doesn't work because there exists a configuration. But what I'm hearing now, and the answer is, it's kind of a limitation of the optimization approach to do everything jointly at once. And so you're conditionally, like under the condition of this one, the optimize the next one to complement that. That's what makes this work.
Yes.
And in theory, God's optimization algorithm could have found that.
That's true. God's optimization algorithm might have found something, although it's not clear. I mean, we looked into it in quite some depth, and we can discuss it in more detail later. it's not clear that God's optimization algorithm certainly would have found the parallel portfolio of size 2, and it would have found, as Kevin just hinted at, something better than we found, right?
Right.
We saw some evidence that God's optimization algorithm might not have found something that's better overall across the set, right? So what would have happened is that it would have gotten quite a bit better on many, many instances, but catastrophically worse on others. And that's why this idea still works, right? So you don't improve performance on an aggregate scale, but you sort of push it into some corner where it's more specialized, and then you can tackle the other corner with the second copy, basically. That's what's happening. We can discuss this more when we're done, but I'd like to just take 10 minutes or so for the third part, because I think you will find that interesting, because it opens the door to, I think, many interesting new developments. So this is in some sense the most open-ended part of what I'm going to talk about. And so this is where, after doing robustness for a while and bringing all the little tools and tricks in our toolbox to bear here, and demonstrated that we could do interesting things. And it's not as trivial as it might sound. It's not just take the tool and apply it. You need to do a little bit more work. But here, we basically went and said, let's look at this formulation to start with and see whether perhaps there is something missing here. And I believe there is. So this is what we talked about earlier, right? Where we say, for all inputs x that are within some given distance, measured however, but usually people take the L-infinity norm, then you should get the same predictions by this neural network F or any other mechanism for classifying, right? And so the question really to ask is, which of the X are most vulnerable, right? That seems to be an incredibly important question. And so that goes then towards three important concepts. It goes towards the critical epsilon, which we independently defined in parallel with another group, and then so-called robustness or critical epsilon distributions. And that has just appeared in JAIR earlier this year, joint work with my colleague Jan van Rijn in Leiden and our PhD student Adversarial Bosman. So here is, a cartoon of a classification, of a binary classification problem and a classifier indicated by this dashed line, right? And as you can see, it's a perfect classifier, at least for this set. We can perfectly separate this. So now let's look at this data point here, from which I have drawn a little arrow. This is the data point that's actually closest to this decision boundary, right? And of course, what we can see is that if we move that data point a little bit, this is the one we should probably be most concerned about, right? So that's already an interesting little insight. So now let's imagine there is a little epsilon multidimensional ball around that point. And you could say that everything within that epsilon ball is a safe perturbation, right? Anything that happens there is still away from the decision boundary and therefore will not cause a misclassification. Now, if you make this ball larger, then it will start protruding to the other side of the decision boundary, and then you might have a problem, right? Still, many perturbations here will be safe, but now there are perturbations that are unsafe and that cause misclassification, right? Good. So let's stick with this radius, which is safe, right? And so now let's look at the entire set. And what I want to explain to you is the concept of robust accuracy, which is what you ultimately care about if you say robustness matters. So just optimizing accuracy with your ML algorithm is not enough. So robust accuracy is defined as follows. I won't show you a formula, but rather show it in a cartoon. Let's look at this thing here with all its epsilon balls. So this is perfectly accurate, and it's perfectly robustly accurate as well, because none of the epsilon balls intersects the decision boundary of that particular classifier, right? Now, if we look at a different classifier, that might be different, right? For the same epsilon balls, this other classifier is no longer perfectly robust, right? Accurately robust. So it's still perfectly accurate, but it's not robustly perfectly accurate. You see the difference? Good. So now, of course, if you make the epsilon balls larger, if you allow more perturbation, more pixels to be changed in your images, right? Or more aggressive filters on your audio samples, then things will get worse. Because now more of these epsilon balls will intersect the decision boundary, and therefore these samples can now be moved to the other side and become incorrectly classified samples. Everybody with me? Good. It's not hard. So now what we did is actually a very simple thing, and it's very surprising that nobody had done it before, and I couldn't believe it when I first sort of came upon the idea, but we checked very carefully, and then the JAIR reviewers checked very carefully, and indeed it's the case. Basically, we said, let's not look at the maximum perturbation that will lead to classification, to misclassifications, but let's do this on a per instance basis. Let's look at every instance, right? And that is equivalent to measuring the distance of the instance to the decision boundary, which of course is not an easy thing to do. And that gives you so-called critical epsilon distributions, right? So that distance here is the critical epsilon for this instance. And now you can compute this for all the instances, the blue ones and the orange ones. And then you get distributions here shown as CDFs. I love CDS, and if you want to challenge me on that, please let's have a conversation and I will convince you. So these are CDFs for two different neural networks, and what you can see first of all is the critical epsilons. They vary hugely, right? As might not be too surprising. Some of these images, in this case, are super sensitive to adversarial attacks and others are not. So that is an interesting insight. Now, unfortunately, measuring the critical epsilon is expensive, which is probably why nobody else has thought about it before. Maybe somebody thought about it and went like, too expensive, let's move on to something different. But if you're smart about it, and we won't have time today to go into technical details, but of course you can read them in the JAIR paper, then you can discretize this problem somehow smartly, and then use something called k-binary search and use a local robustness verifier in a smart way to measure this, or at least to get good bounds, right? And that's all you need. And this then gives you a more nuanced and realistic picture of local robustness. And that is incredibly useful for comparing neural networks now on a more fine-grained basis and for assessing the impact of robust training, which is what you would have to do in order to get rid of the problem of a lack of robustness. So I just want to show you some actual data from this so you can see that this is actually, it's revealing important differences between networks. So here we have 12 ReLU networks that were trained on EMIs, a very simple data set, very well understood. And 100 images were selected uniformly at random to make it computationally tractable, because it is very expensive, unfortunately. Then we measured the critical epsilon distributions on training and testing sets, because of course, if whatever you do only holds on training data and then testing data is totally different, then you have gained nothing, right? And so here is what you find. These are the two networks. And in this case, we show the critical epsilon distribution not as a CDF, but as a point cloud here. And then a little box plot overlaid. So the box plot relates to the points shown behind it. And we chose, just for illustration purposes, two different critical epsilon values that have been widely considered in the literature. Those are these two red lines. And what you can see now is that these critical epsilon distributions, right, for the lower value, the sort of smaller perturbation, loud perturbations, would have told you that this net classifier is perfectly robust, right? And this other one is almost perfectly robust. And it would have also shown you that for this larger boundary, things of course change a bit, but what it wouldn't have shown it at all is that actually there are some instances that are very close to being non-robust here, right? And there are a lot of instances which are extremely robust here, right? So now we can do this on many different networks, and you see that these distributions, I now show you only the box plots, are really hugely different. And that's all on the same data set, right? So different neural networks, all on the same data sets, hugely different robustness distributions, although for many of them, the median and the mean are actually reasonably close to each other. And you even found cases like this here, very naturally, where two networks, again, trained on the same data set, where these distributions start to cross over, right? Meaning that, essentially depending on what robustness level you look, you would prefer one or the other, right? So it's not even the case uniformly. In other cases, it's basically uniform, where for any robustness level, one is better than the other. Good. For training versus testing data, which I said is an issue, these are pretty close. So if you actually do a statistical test, you will find that there's no significant differences between training and testing, which is good. So it does pay off to measure this on training data because it does generalize to testing data. And you see the same thing on here. So this is a relatively small neural network architecture. What you see here is when you use adversarial training, in this case, a very well-known algorithm called diffAI and another one called PGDK. That one here is actually considered state-of-the-art. The other one is close to that. What you can also see is that indeed, on average, or on median to be more precise, adversarial training doesn't do very much. What adversarial training does is it removes sort of the most vulnerable points down here. The points where even the smallest perturbations can do quite a bit of damage. And what's very interesting, if you look at this now, is these are the CDFs underlying this. And point is not adversarial trained, normally trained. And then diff AI and PGD are the adversarially trained versions. What you can see here is, again, that the lower end of this distribution is shifted as it should. But on the upper end, right, you even get some small, in this case, not statistically significant losses, but you do get some losses in robustness. And the same holds on the testing set, of course. So when you now go to more challenging examples, what you find is that PGD becomes more effective because it's actually made for challenging examples. Whereas, and it depends on this parameter that we have here. Sorry, just go back here. It depends on this parameter here that essentially controls the step size in PGD. So what you can see here is that, again, PGD is actually pretty effective in removing these problematic cases here, which sort of break robustness for natural training. But for this parameter value, it actually does more. It shifts the entire distribution up like this, which if you just look at whether it's robust or not, if you just look at robust accuracy, you would never observe the advantage of this parameter value 0.3. So that's kind of nice. Okay, to wrap up, comparing networks on these critical epsilon distributions is actually very interesting because you do observe starkly different critical epsilon distributions between networks, and it allows you to distinguish things that previously looked basically the same, right? Including adversarial training methods. We do observe similar critical epsilon distributions between training and testing data, which means the stuff generalizes and is therefore practically useful, at least in that respect. And it does give you new insights into the effects and also the efficacy of adversarial training methods, as I've shown you in some simple examples. So taking a step back and looking at the three topics that we talked about today, the AI revolution is basically a transition from explicit to automatic programming. Machine learning and neural network robustness is the key to responsible use, because obviously there are many applications where if your machine learning method is not robust, you have a problem. And robustness verification, which is the technique for assessing or for certifying that something is robust, they actually do require advanced reasoning techniques and also adaptation to diverse network architectures and use cases. The kind of things that people have been studying, not forever, but now for a good 15, 20 years, namely automated algorithm configuration, portfolio construction, and performance prediction, are key to the next generation of neural network robustness verification, right? We could make progress in a field where quite a few other groups have worked very hard to push the state of the art by using these techniques, not out of the box, but not so far from out of the box either. So this is good. And I believe, therefore, the use of techniques like this really lies on the critical path towards safe, reliable, and sustainable AI, which is exactly what, at least in Europe, has been politically and scientifically decided is the kind of AI techniques that people want. And it's the kind of AI techniques that we don't get out of the United States and the companies being active there, nor out of China right now. This might change, of course. For instance, if they read this work and find it as exciting as hopefully you do, here's hoping, right? Or if they start making really bad experiences, which now seems to be starting to happen, especially in commercial settings, right? So I would place a rather big bet that this focus on safe, reliable, and sustainable AI, in case you wonder about sustainable, this is getting the same kind of quality of results with less compute, right? Because compute is a big cost factor in all of this. I would say this focus will deepen and broaden, right? And so therefore, it's one of the reasons why I think the AI in Europe currently is on a very promising path, although by other metrics, it's actually quite far behind what's happening in the US and in China. It will be very interesting to see where Canada finds itself in this sort of value-based discussion, what kind of AI techniques we want to have. But it's been a pleasure and a privilege to have the chance to talk to you guys here about it. And my hope is that maybe one or the other will be inspired by this and think even more than you already do about what needs to be done in order to drive us in this direction. Here were some ideas, but there are many, many others, and it would be fun to talk about them individually. individual. Thanks.
All right, we're 5 minutes before the hour. I know some of you might be running off to another appointment, so maybe let's give people just a moment if they need to clear out. And then I know also many of you have questions for Holger that
Yeah, there is still food, and I believe the food is also there to be eaten, so that's maybe another incentive to stay a little longer.
All right, and maybe let's take a question. Maybe let's start with people we haven't heard from during the talk. I've got a question too, but I'll also apply the rule to myself. Greg, yeah.
What kind of changes would you want to see in neural network architectures to make the verification process easier?
What changes to neural network architecture makes the problem easier? If I knew there would be a piece of works, or more importantly, maybe a JMLR paper, the answer is we don't know. We have research going currently on neural network architecture search with the objective of basically minimizing the verification effort. And that shows clearly that, you know, the architecture plays a role, as you might expect, but sort of a deep understanding of that, sort of especially an a priori understanding, so that you don't need to experiment, right, automatic or not, is, as far as I know, lacking. So this is a great research direction, and I'm sure it's an area where several PhD theses can be successfully written and defended. So great question. Sorry that I don't have a really good answer yet.
Inspiring talk. So classification is the key task, but about like set of tasks where the input and the output are very complex. So I was wondering your aiming for robustness in those cases. We check by trying to extract classification tasks for those kind of network and use all these powerful techniques that you are presenting, or you think we need something?
I personally think you need something different, right? You can probably do some reduction as you suggest, but my feeling is that this is not the best thing to do. And maybe the easiest way to see this is if you think about regression and robust regression, right? What does this even mean? Because now there's no decision boundary, so we can't measure distance to it, for example, we can't optimize distance to it. All of this doesn't work anymore, right? So instead, what you have is basically sensitivity to change, right? So what you want there is, if you change the input within some epsilon ball, the output should not change more than, you know, some delta, for example, right? That becomes conceptually related, but actually different problem for which you, I would say almost certainly, in order to be really good, need different techniques. And that's still for sort of simple data. So now if you have more complex data like natural language, for example, the question is even how do you measure this sort of deviation in the output and the input, right? And actually a person like you might have great ideas about that. And I personally believe if you wanted to apply something like this to Gen AI settings on natural language, which of course would be an obviously interesting direction, it would benefit from close collaboration between NLP people and people who do verification, right? Because I think you would need a better understanding of what even constitutes critical changes, for example, right?
Oh, yeah, sure. So really excited with the critical epsilon distribution work. Now this pushes me in the area, like I've never been a continuous math before. I'm not a continuous math person at all. But it feels like have you explored, there's some sort of geometric interpretation here, right? Because if you think about, like just to give it like in a single dimension, a classifier that just says, you know, greater than or less than, it's going to give you amazing robustness.
Yes.
Okay. But a classifier that says irrational, rational will give you this distribution that says, and again, my math would be like, but you know, whatever, 0, epsilon, everything is completely unrobust.
Yes.
Right? And so it seems like it characterizes sort of how clean the classifier is in that geometry. Is there any problem? I mean, have you explored this? Is there problems to kind of really look at how sort of geometrically clean,
Yes.
or topologically like less islands or something?
So we have looked a little bit into that so far without great success, but with some interesting small insights. what you're really getting into is studying basically the geometry of decision boundaries, right? And of course, that also is a topic of great importance for understanding why, for instance, deep neural networks work reasonably well in the first place, right? Robustness or not, right? So this clearly is a very important topic. I'm not sure, maybe David even knows more about it, because it's a geometry thing, very high dimensional, sort of messy, right? What we try to do is apply some landscape analysis techniques to the decision boundary, but it's computationally all extremely expensive, right? And so I think this is where you get to the boundary. There's some old results from statistics that talk about sort of much simpler, we should really call them ML techniques, but they just call them regression techniques and whatnot, right? That of course by construction have clean decision boundaries, and then you can do more, right? So notably, and it's good that you sort of indirectly called me on that, for a simple cartoonish example like the one I've shown you, which essentially suggests let's just use some sort of linear separator, you would never do what I talked about, right? So there, I think you can solve the problem just in math. But of course, who uses nowadays, linear separators? I think what this suggests, however, is there's a tendency right now to train as large a network as you can on pretty much anything, right? And that might be wrong. It might be wrong not because it's overkill or it's maybe doesn't generalize as nicely as it should. For all of this, I think there are reasonable solutions, but it might be wrong because making sort of deeper observations and then also giving better guarantees on robustness might be much, much harder in these situations, right? And so one thing, which is why I'm very grateful for your question, that I really, truly, deeply believe, although of course I could be wrong too, is that the focus on robustness will revive a focus away from let's just scale up, neural networks, towards let's do something that maybe is also more explainable, more understandable, and maybe fairer in a certain sense, and that would be good.
So I've got a question about your second part of your take-home message about robustness being important. You didn't really dwell on quite how this works, and maybe my understanding is wrong, but my understanding of how these adversarial examples get found is that you need to run an expensive optimization procedure against the neural network to find some very unlikely edge case that causes the neural network to do something weird. So it's sort of terrifying to see something that looks to us like a stop sign that gets classified as $120 an hour, but there might be essentially zero probability that the Tesla camera would ever encounter such a situation in the world because its supported distribution might be tiny. And I know you're a guy who for years very loudly argued that worst case analysis shouldn't be our focus and we should care about what happens on average. So I wonder why this kind of robustness should bother us.
Well, first of all, I'm the kind of guy who says look at the entire distribution. So the worst case is just one part of that. I wouldn't say let's just look at what on average, right? I think that's a problem too. So, but in any case, you're of course right. Two parts to the answer. The first is, even if you cannot get insights into the Tesla camera, and I'm sure many people have a lot of incentive, a perverse incentive to get deep insights into the Tesla cameras and the image processing software after that in order to inflict damage, right? But even if you believe that this is hardened so that you can't do it, there have been examples in the real world where you can manipulate the traffic signs by placing stickers on them. For the computer vision, state-of-the-art computer vision systems that way. So you can't necessarily protect the world, all the traffic signs, on UBC campus against that kind of tampering, right? So there is unfortunately a lot of incentive, especially with military applications, which of course people are now looking at, of tampering in any way you can. And by just hardening the system itself, it's not enough. You would have to harden the world also, and that's often impossible. That's number one. But number two, and more importantly, what's good about worst case results is that it basically bounds what can happen in the real world, right? And as you noticed here, especially with critical epsilon distributions, we don't necessarily need to guard against everything, but we should be able to quantify how much we guard against reasonably, right? And then there is, of course, an assumption that what you guard against, somebody will manage to exploit it. And there is unfortunately evidence that sometimes noise is enough, right? And this is sort of black swan effects, and I wouldn't go out and say this is the reason, but there is an analogy here. You know that due to the Tesla vision system, some people now die, right? Because the Tesla vision system didn't see a truck, for instance, and then or misclassified it, and then the car goes underneath the truck, and basically people died. Well, I wouldn't say there's anything like an adversarial attack involved there, of course not, right? But what I would say is this 1 in a million chances, right? If you have 1 million cars on the road, sooner or later it will hit someone, and that's a bad idea. Yeah? So from that perspective, I do think for certain safety critical applications, not everything in the world, right? It is important to give worst case guarantees. Yes, and these worst case guarantees are less unrealistic than the ones in the case of NP-hard problem solving, for example, because they do seem to occur in certain not unrealistic situations if the sample size gets high enough, which it does if millions of people use it all the time.
I think that all sounds pretty convincing. I think your first point about stickers on stop signs sort of makes me think that there's another kind of robustness that's interesting to study, which is the robustness of an adversarial attack, right? Like a sticker on a stop sign has to work under slightly different lighting conditions and slightly different angles. And so it means that it's it isn't just some like very edge casey thing. And I would think robustness to attacks that are themselves robust would be a lot more important.
I completely agree with you. And what I didn't mention here, although you could have seen it in some of the data I've shown, is there are actually differences with that sort of concept in mind, right? Differences between various adversarial attack techniques, which we have started to study and also design, but also differences in terms of the generalization and the generalizability of the attack, whichever way you found it, right? So the attack is basically just a perturbation. It's not the mechanism that produced the perturbation. So when you say this is the perturbation, how robust is it? People have studied that and they found that some are more robust than others. And you're absolutely right that those in some sense deserve more attention, yes. So robustness distributions, by the way, can also help be a little bit more nuanced there, which is why I like them.
Cool. All right, let's leave it there. Thanks everyone for